Okay, in this video tutorial, I'm going to show you how to use Jupyter Notebook to analyze ERP data. Show you a little bit about Jupyter Notebook as well, and also show you how to do the range scale procedure in R if you wanted to do it that way. So first, starting with the Jupyter Notebook, I have an R version running. You can start this and you can just start adding cells and text. The cool thing is you have Markdown and then you have code that can be executed. So if we want to add a new cell, for example, we can add whatever we want and we can change the size of the text by using the number of hashtags. And you can put text in there, and this is what you call Markdown. So if you change the cell type to Markdown, it then becomes text. And when you run it, it'll become text. And you can add notes to yourself, and you can delete these if you want to. You can add notes to yourself, like here I've designated what the time interval is for this particular set of analysis, okay? So then in the other kind of cell, the code executable cell, you're going to type your commands. So these are libraries that you want to load, and AFX is great for doing analysis of variance. Tidyverse has a lot of data filtering and handling capabilities, so that's why it's in here. And so what we're doing is we're creating a data frame called data1, and it's going to read in our data file. Now this is in the same directory as this Jupyter Notebook, so we don't need a full path. I just put the name of it, and then the separator, of course, is a comma because it's comma delimited, and it does have headers, so we set that to true. So it'll read that first row in your data file as a header. And I guess I'll just, in case you didn't see the other video, but this goes with the other video. So I'm going to show you what the data file look like. This is the unscaled version, and as you can see, you have a header here with a sub-ID, electrode, prime, type, volts, and then our data. This is what you call long format, and we created that in the previous video. So we're reading that in. Now, one thing you have to do is you have to change some of the factors, or at least I like to make sure that all of the non-numeric variables are changed to factors. Now, this str command for your data frame will give you the structure of your data frame. And so you can use that to check and see, like, is it calling a string variable like it should, or is it determining it as a factor? I found while working with this that it's just easier to go ahead and set them and call all these different variables as factors so that we can put them in our analysis and use them. So you are going to use sub-ID. This is going to be a random factor in your analysis of variance. So you go ahead and set all of those as factors, and then we can start to work with our data a little bit. So one thing I'm going to do is right now have all of the electrodes are input. There's no ordering information in those electrodes. So I'm going to go ahead and create a second data frame. We're going to call it data2, and we're just going to make it equal to the first data frame. And then we're going to add some new variables, and we're going to set the value, default value, to 1. And we're creating a variable called AP that stands for anterior posterior position. And we're creating a variable called LR, which stands for left-right position on the scalp. And what we're going to do is we're going to focus on the electrodes, like in this 25 electrodes in this array, where we have 1, 2, 3, 4, 5 rows of anterior, posterior. So like 1, 2, 3, 4, 5. And we're going to give them values 1, 2, 3, 4, and 5, depending on what row they are in. And this is, of course, the way the electrodes are laid out on the scalp. And we also have left-right row, or column, I should say, 1, left-right column 2, left-right column 3, which would be the center or the vertex, and then 4, and then we have 5. So what we can do is we can assign values to each of these, and we could create clusters if we want, location clusters if we want. So if that's something that you're doing in your analyses, it's easy to do. So once we set everything to 1, we now have to then recode our variables. So how do we do that? We're going to use this mutate command, and we're going to change data and data2, and we're going to change anterior, posterior, and then cases. And so when electrode is F7, we're going to give it a value of 1. And this statement continues on for a while. F3 is going to be a 1, FZ is 1, because they're all in that first row, right? And F4 is 1, and then F8 isn't 1. But then when we get to the next row, like with FT7, we're going to give it a value of 2, and so on. So that's how we recode our anterior, posterior variable. We're going to do the same thing for the left, right, but we're going to obviously use different codes. And so F7 would have that 1 value, F3 would now have a value of 2 because it's in the second left, right row, and so on. And so then if we want to use those in our analyses, we just have to create them as factors. So we're changing them to factors here in our data frame, and boom, we could use them. We could put them in. Now, one thing I'm going to do right here is the other thing that I'll frequently do and others frequently do is just not use every electrode, but single out some electrodes. So this is an FN400 analysis. So for that, I'm targeting the electrodes F3, FZ, F4, and then we have C3, CZ, C4, and then we're going to have P3, PZ, P4, because actually what we're going to do is look for differences in FN400 or N400. We would keep that little electrode array. So that's the electrode array that I'm analyzing, and you can just use this filter command and filter the data however you want to filter it, and then analyze it. So you can create as many of these data frames as you want and filter it however you want virtually, and you can always go back to the original data frame. That would be data frame 1 if you want to start again, which is the nice thing about it. Now to analyze it, it's very simple. We're just going to create an object. In this case, I'm just calling it AOV, which stands for Analysis of Variance 1. And we're going to use this AOV or Analysis of Variance EZ command. This is from the AFX package. The first variable that we put in is our random variable, which is our subject identification number. The second variable is the dependent variable. The third entry here is the data frame you want to analyze. Make sure that that matches up. So data frame 3. And then we specify whether they're within or between subjects variables. And in this case, they're all within subjects variables. And so you can change these to meet your design needs as well. So that will run the analysis, and it'll put the outcome of the analysis of variance in this object AOV1. If you want it to look at the output, you need to have it printed. You could just type AOV1 and then it would print the output. I like this nice command. I think it's from the Tidyverse package, and it presents a nicer table. And so we're going to do this object. But the nice thing is you can specify, or the nice thing about the nice table is you can specify a few switches here. So for effect size, we're going to use partial eta squared. And we're going to go ahead and apply corrections, Geyser greenhouse correction. So it'll do the Geyser greenhouse correction right for you in the table. You don't have to do that. And we're going to suppress the mean square error. Of course, if you wanted to see the mean square error, that would be another entry in the table. And so we're going to get a table out. Now, the other thing you might want in some of your analyses is actual cell means. So if you want that, you got to compute them. And so I'm creating this variable called cell means, and we're going to take our data frame and we're going to group it by our variables. And so you could change this if you want to create different groups. We're grouping it by our variables. We're going to summarize, and we're creating a variable called microvoltage, and it's going to be the mean value of our variable volts, and we're going to do standard deviation, which is a standard deviation of our value volts, right? And then, of course, to see it, you have to output it. So that's what the cmeans command does, is it outputs it. So let's look at the output of all of this text. So the nice thing is that's our code. We can run it. And when we run it, we get our nice table here. So here's your table. Here's your effect, right? Here's your degrees of freedom, and they're corrected degrees of freedom based on Geyser greenhouse corrections because we specified that. Your F value, your partial eta squared, and of course your P value. That comes out. So there's your output, and you can save this. And when you save this notebook, you can always come back to it and it'll be there. And it's dynamic. So if you change something in the analysis, this would change as well. Here's our table with our means. So if you want the means, you know, here they are for each one of the rows. So this would be anterior, posterior, row 1. The second one, like the central position, and this is more the parietal position. And you can sort of see how the topography differs just based on that anterior, posterior electrode, right? So that's that table. So that's how you would do that for a conventional analysis. Now, if you want to do the scaled data, it's trivially easy. And really, the cool thing is you can copy this code. You can copy it and paste it into a new cell. And so that's basically all I did. You change the file name. Now it's the scaled data file, loads it up. You can run it. That's it. Now, the one thing you want to do for a lot of scaling, if you're looking at the scaled data, is generally you're comparing two conditions together to sort of see, does the topography differ? So in this case, what I did is I filtered it for prime, and so it's going to filter the data frame. So it's going to just focus on the unprimed condition and our orthographically similar non-words. So basically, I'm isolating two primes here in that massive data set that had at least 3 primes, if not more. I think it was just 3 primes. And we're also going to then filter and just focus on hits. So we'll forget about correct rejections. We're just going to see, does unprimed hits, does it have a different topography than the OS non-word primed hits? And we can do that. And so all we're going to do is we're going to substitute. The key thing that we're substituting in here is data 3. That's going to be in our analysis. Now, the other thing that changed is in that data file, we didn't have volts. We had our dependent variable was called scaled. So you have to pay attention to that. And then, of course, our design is we just have prime and electrode. We don't care about any of the other conditions. And that's what we're interested in. The rest of the commands are the same. And so then you're going to get your output and you're going to get your prime, your electrode. The key here is the prime by electrode interaction, is it significant? And in this case, it is. And that would be evidence that the topography differs for those two conditions. So that's how easy it is to do. And you can keep adding cells. I'll add cells for all kinds of analyses that I do, different time intervals. And I just, mark them with markdown text so I can follow along. And then you change the file names and that's it. It's very simple. And you can save it and you can always go back and look at it, reload it in Jupyter Notebook, and it's there and you can find it. Now, I did want to show you real quick, what if you had some data in R, but you didn't do the Python version that I showed you and create range scaled? You can do the range scaling within R, and this is what this code does. So I'm not going to belabor this because this is all the same. What's different, though, is you take that first data frame that we read in, and we're just going to call it original data frame, right? We're going to set our number of electrodes. Now this, if you watch the other video that showed how to do this in Python, you're going to see a very similar logic. We're going to loop through in chunks of electrodes to range scale each condition. In my array, I have 29 electrodes, so I'm going to set that to 29. And then what we're doing is we're creating a transformed data frame. We're just making one. It's empty. Now I want to do a little check, and this is just to head off any errors. And so your data, the length of your data frame should be equivalent to all of your number of electrodes, like a certain number of times through, depending on how many experimental conditions you have. And so this just runs that check. If it's equally divisible, no problem, it'll go on. If it's not, it's going to give you an error message and say like, hey, it's not adding up. Something's wrong there. It'll give you an opportunity to investigate and make sure that it's working right. Then what we're doing is we're calculating, assuming that we pass that check, it's going to do some iterations. It's going to determine how many iterations through the data. This is just based on the original data frame length divided by the number of electrodes, right? So our original data frame divided by 29 electrodes, that'll give you the number of times you got to go through the data set for the scaling procedure. So we're going to create a loop here, and it's just going to go through the number of iterations. We do something similar that we did in the Python version, where we're just basically finding a starting index position and an ending index position. In this case, you're starting by where you are with the number of electrodes in the loop. So the loop, and we're going to go with the number of electrodes. Same thing for the ending index place. And then we're going to create a chunk of data where we basically just chop out either the starting and ending index. That's the chunk we're going to focus on. We find the minimum value, we find the maximum value, and then we're going to create a variable called scaled, where we subtract the minimum value and divide by the difference in the two. Easy peasy. And then all we have to do there is, once we have the chunk data, is just we put it in this thing called transformed group. That's going to save our data that we've rescaled here. We have scaled, sub-ID, electrode, prime, etc. And when we're done with that loop, we're going to, then we bind it to our transformed data frame. And so when we're done with that loop, we'll end up with a new data frame called transformed DF that will have all of the scaled data in there. And so now we can do some analyses on it. So again, just like I did before, we're going to filter for unprimed and OS non-primes, and we're going to filter it again for just hits. And then we pop, but notice that the first one, we're filtering the transformed data frame. So we're filtering that, and then the second time we're filtering the second data frame, and then we're passing it through. All of that is the same. And if you look, we get the exact same values here from doing the calculations within R that we did within Python. So everything, checks out with that. But that's the text that you could use if you were stuck and you wanted to go ahead and transform your data frame. You could modify that for an existing data set as long as it's in R and go ahead and do that range scale transformation. So I hope you've found this helpful. Thanks for watching.